Welcome back. We were discussing in Fundamental of Electronics the special purpose diodes. We have covered the fundamentals of linear diodes in the lecture 4A. This is lecture 4B, where we will focus on further information on linear effect and its regulating effect. So what is the difference between linear effect and avalanche effect? Avalanche we have seen in the first lecture of diodes. So the linear effect occurs in heavily doped diodes. We have seen that doping is basically adding of the impurities as of N-type semiconductor or P-type semiconductor. So when doping is heavy, then there is a narrow depletion layer. The electric field becomes intense approximately around 3 lakh volt per centimeter. So the electric field will pull the electrons from the valence orbit. Valence orbit means the last cell in an atom. It is known as high field emission. So this high field is resulting the valence electron to be pulled out, and that dominates the breakdown voltage to be less than 4 volt. So the breakdown which is occurring for the diode, we have seen in the lecture 4A that in the linear diode the breakdown will be in the reverse biased. So the voltage which is less than 4 volt, there only the breakdown will occur because the intense electric field is there. Whereas in avalanche effect, it is the minority carriers which are accelerated, dislodging the other electrons. So minority carriers means if you have the P-type semiconductor, then the electrons become the minority carriers, whereas if you have N-type semiconductors, then the holes become the minority carriers. So it causes an avalanche of free carriers resulting in large reverse current. So these minority carriers are resulting in large reverse current, and that will dominate the breakdown voltage, which is usually greater than 6 volt. So here we are saying that it is less than 4 volt in linear effect, but in avalanche effect, it is greater than 6 volt. So what is happening between the 4 to 6 volt? So you will have both the linear effect as well as avalanche effect will be present in the semiconductor material. So how do we name them? So historically, we say that all breakdown diodes are basically the linear diodes, even though both effects may occur in this. So even the linear and avalanche, both effects are present, but the diode name that we'll be giving is basically the linear diodes. Next topic, we have the temperature coefficient in linear diodes. So what is the impact of temperature on linear voltage? Linear voltage changes with ambient temperature. Ambient is the atmospheric temperature, and it is listed in the data sheets on the temperature coefficient. So how do you define this temperature coefficient? It is basically the change in the breakdown voltage per degree centigrade temperature. So temperature is measured in degree centigrade. So breakdown voltage less than 4 volt, which we have seen in a linear diode, you have the negative temperature coefficient. So in linear effect, you will have negative temperature coefficient. Let us take an example. A 3.9 volt linear diode may have a temperature coefficient of minus 1.4 millivolt per degree centigrade. What is the meaning? Meaning is for each 1 degree centigrade increase in the temperature, there will be breakdown voltage which is decreased by 1.4 millivolt because you have a negative sign. So that is basically given by the decrease in the breakdown voltage. Whereas the breakdown voltage greater than 6 volt, when you have the avalanche effect is present, then you have the positive temperature coefficient. So again, let us take an example. So if you have 1.62 volt linear diode, it can have a temperature coefficient of plus 2 millivolt per centigrade temperature. Meaning 1 degree centigrade temperature increase, the breakdown voltage will increase by 2 millivolt. So when you have positive temperature coefficient, then breakdown voltage will increase. When you have negative temperature coefficient, then the breakdown voltage will decrease. So between 4 and 6 volt, the temperature coefficient shift from negative to positive. So there is a shifting from negative to positive. Some diodes have a 0 temperature coefficient, offering stability across the temperature ranges. So diodes may have a 0 temperature coefficient, and that is important for application that is needing the stable linear voltage. So if you need certain stable linear voltage, then you may go with 0 temperature coefficient over wide temperature variations. Let us see the problem number 2 from lecture 4b. You have to find whether the Ginier diode in this circuit is operating in the breakdown region, yes or no. So if you see the circuit, you have a source where 18 volt is there. Internal Ginier resistance is 270 ohms. And there is a Ginier diode whose breakdown voltage is 10 volt and a load resistor is given to be 1 kilo ohms. So the Thevenin's voltage we can find out here, and the load resistor, which is equal to 1 kilo ohm multiplied with the source voltage, that is 18 volt, divided by sum of the resistances, which is 270 ohms plus 1 kilo ohm. That gives to be 14.2 volt. So this is how we find out using voltage division rule we have discussed in lecture 4a. Now, what is the indicator? Indicator is that the Thevenin's voltage is 14.2 volt, which is greater than the Ginier voltage. So Ginier voltage here is 10 volt, but you are getting 14.2 volt as the Thevenin's voltage. So it means that the Ginier diode is operating in the breakdown region. Next problem, we have to find the Ginier current for the circuit shown. So you have a power supply whose output is 18 volt and the Ginier breakdown voltage is 10 volt. You have a load resistor of 1 kilo ohm and the resistance internal for the Ginier is 270 ohms. So what is the current which is flowing from the source? IS. So IS we can find out as the source voltage, which is 18 volt minus the Ginier breakdown voltage 10 volt in this loop divided by the resistance 270 ohm. So this gives 29.6 milliampere. So this is nothing but delta V divided by the resistance R, which gives the current IS. Now what is the load current that you have? What is the current flowing here? IL. This current will have the same voltage as the Ginier diode because both are in parallel. So you have 10 volt divided by the resistance of 1 kilo ohm. Here it is given 1 kilo ohm. So that makes 10 milliampere as the load current. Now you can apply the KCL equation here to find the Ginier current. So Ginier current is nothing but the total source current minus the total load current, which comes to be 19.6 milliampere. So that is the Ginier current. Next problem, we have to find the behavior of this circuit. So what is the behavior of the circuit? You have a power source output given to be 35 volt. Now you can see that there is a set of Ginier diode and internal resistances which are connected. So these are the two sets and you have the load resistor. So first Ginier diode will act as a pre-regulator. So we have already studied pre-regulator in the previous lectures. So this set will act as pre-regulator and second Ginier diode will act as Ginier regulator. The second diode will act as Ginier regulator. It means the pre-regulator output, if you see here, this 20 volt. So this 20 volt will become the input to the other regulator. So Ginier regulator output now will be 10 volt. So 10 volt is the Ginier regulator output. Provide the second regulator within a well-regulated input. So you required a constant voltage of 10 volt. Ensure that the final output is extremely well-regulated. So whatever the circuit we are using the pre-regulator and the Ginier regulator, you are getting a constant voltage and extremely well-regulated voltage. So problem number 5, let us see. So you have a circuit, you can see here two back-to-back connected Ginier diodes are there. So Ginier diodes are commonly used as voltage regulator we have seen, and this is remaining in the breakdown region. So Ginier diode will operate in the breakdown region as a voltage regulator, and they can be utilized in circuit for wave shaping. So we have seen in lecture 3 about different wave shaping circuits, and these configuration will have two back-to-back Ginier diodes, so that are connected back-to-back. So you may have positive half cycle and negative half cycle operation depending upon what is the source you have, which is having the maximum amplitude of plus Vp. So positive half cycle, the upper diode, whatever you have here, will conduct, and the lower diode will be in the breakdown region. So this will be in the breakdown, and output will be clipping at Ginier voltage of plus 0.7 volt. So this is the forward voltage drop 0.7 volt. So here you can see that the clipping that you have is basically at plus 0.7 plus the Ginier voltage Vz. Whereas in the negative half diode, reverse process will take place. The lower diode will conduct and upper diode will be in the breakdown region. So the output approach is square wave. So here you have minus Vz minus 0.7, which is nothing but minus of Vz plus 0.7 volt, which you are getting it. So what is the conclusion? That you will get larger sine wave produces a better shaped output square wave. So you are getting a square wave at the output. Input is basically a sine wave, and these two back-to-back connected diodes will be acting as a clipper circuit for voltage shaping. Problem number 6. where we discuss about the multiple DC output voltage. So here you can see that there are multiple DC output voltage when we are having the normal diode and the Ginnier diode combination. So you have a combination of Ginnier diode and ordinary silicon diodes which are used to generate multiple DC output voltage from a 20 volt power supply. So you have a voltage which is 20 volt as the power supply, but the output that you are getting is having different magnitude of the DC output voltage with the combination of the Ginnier diode and the ordinary silicon diode. So the bottom diode, if you see here, which is basically the Ginnier diode, so it is giving you a voltage of 10 volt, and the forward bias silicon diode here, which is 0.7 volt. So the total voltage that will be 10 plus 0.7, that is equal to 10.7 volt here. And similar operation again will take place here, which will add plus 0.7 to get 11.4 volt, and then you will add 2.4 to get 13.8 volt. So different combination of Ginnier and silicon diodes can yield various DC output that you may need at the output of a circuit. Now you need a certain protection of over voltage. Like for example, here you have a relay which is connected 6 volt with a Ginnier diode of 5.6 volt. Input is 12 volt. Now output you are getting 6.4 volt. Now how it is possible? So if the relay which is of 6 volt is connected directly to 12 volt supply. So if this Ginnier diode is not there and you are connecting this relay directly to power supply, it might get damaged. So the solution is that you connect a Ginnier diode of 5.6 volt in series with the relay. So the Ginnier diode is connected in series with the relay. This is for protection purpose, and the Ginnier diode drop of 5.6 volt will lead 6.4 volt across the relay. So you have 12 volt as the source, 5.6 volt is the drop. So you will be having 12 minus 5.6, which will give you 6.4 volt here, and the output of the relay is of 6 volt. So it will be protected and it will not be getting damaged for high voltage. Again, you may have over voltage protection using a capacitor. So you have a capacitor here, which is electrolytic capacitor, and it has low voltage rating. So example, let us take 1000 microfarad and rated at 6 volt. So if you are using a supply of 12 volt and the capacitor could be damaged, so you connect the capacitor directly with the supply without using this Ginnier diode, then the capacitor will get damaged. So it is better you put a 6.8 volt Ginnier diode here in series, and the voltage that you will be getting is 12 minus 6.8, which is equal to 5.2 volt across the capacitor. So it means that 6 volt rating is there and here the output is 5.2 volt. So the capacitor will be not getting damaged under over voltage. So in this lecture, we have discussed a little bit more on the Ginnier diodes, which are special purpose diodes, in terms of voltage regulating action and comparison of Ginnier effect and avalanche effect. In lecture 4C, we are going to discuss more on special purpose diode. So stay tuned. Thank you for now.